Okay, welcome to CALOP E10 Learn Seminar. I'm going to introduce today's speaker, me. My name is Kangbok. I'm a professor in the Department of Industry and Management Engineering. Okay, I'm happy to see you guys here. So today's title is Worst Case Analysis by Optimization. So I think some of you have different backgrounds. Some are from math or industrial engineering and computer science, right? Okay. So, but today's topic is very easy, not difficult, because it's the problem nature is just simple optimization. Let me introduce myself first. My background is industrial engineering from bachelor, master, PhD in POSTECH, and I'm also doing a work as vice president of admission and student affairs at POSTECH. And this is my history. After getting PhD, I had to work in the company as a substitution of my military service. And then I decide, oh, I want to back to the academia. So I went to United States. So I spent 3 years at NYU and 3 years at Rutgers University in New Jersey, and then City University of New York. And during the 3 years, total 9 years, I was in business school. And then I came back to POSTECH in 2016. Okay, this is my main research area, combinatorial optimization, and especially approximation algorithm. And more specific topic, the machine scheduling is my main research area. And sometimes it's extended to the supply chain management. Also, for the practical research, I'm doing work on the production planning and scheduling. So these are my kind of portfolio. So some papers are focused on math programming, POM, Omega, EJOR, theoretical computer science, and so on. Also, I had played a associate editor role in journal scheduling, work spectrum, and IJPR. And also I had a project with some manufacturing companies, POSCO, LG, Samsung, etc. So I know some about the theoretical work and practical work. But today is very theoretical work. I'm not sure whether there is some practical application or not, but I'm going to talk about the worst case analysis. And I'm going to introduce the concept first, and then I'm going to give you 3 examples to explain the detail of the worst case analysis. Okay, worst case analysis. What is worst case analysis? Many combinatorial optimization problems are NP hard. What does this mean? It's hard to find the optimal solution. It may take exponential time, right? For example, here traveling salesman problem, knapsack, many scheduling problem, many graph problem, and so on. So we believe there's no polynomial time algorithm, right? So what should we do? There are several approaches. Anyway, we need to get the solution. So one possible approach is exact algorithm. Even though there's no polynomial time, there's no polynomial time, we want to find the optimal algorithm, but it may take exponential time or pseudo polynomial time by using math programming, exponential time algorithm, or dynamic programming, etc. Another area is approximation algorithm. Usually, approximation algorithm is quite easy. But another approach is heuristic. But what's the distinction between the two? Approximation algorithm have worst case guarantee. It cannot be that bad. Theoretically, we have to prove it. But for the heuristic algorithm, there's no theoretical guarantee. However, usually it performs well in real practice. Okay, today I'm going to focus on this approximation algorithm. So approximation algorithm usually polynomial time algorithm. And designed for the NPR problem, the goal is to find the near optimal solution efficiently. So efficiently means we kind of consider polynomial time algorithm. The near optimal means the solution must be somehow close to optimal. Then how can we measure it? So many people use the worst case performance ratio, the theoretical bound on how poorly algorithm can perform compared to the optimal. So many of you already are familiar with this formula. So we have an algorithm A, and we consider all possible instances. One particular instance, we can consider its optimal solution. This is solution by algorithm. We are going to compare this ratio. But this ratio is bounded by a certain value, upper bounded by certain. So you may have a 2 approximation, 3 approximation, etc. So this is the worst case performance ratio. So we want to prove this worst case performance ratio. Okay, let's back to the very original question. What is the meaning of proof? How can you prove some theorem or conjecture? So many cases, people use these two ideas by construction. According to certain property, when you find a certain condition, etc., etc., we can guarantee, oh, the constructed solution must have certain property. Or contradiction. Suppose our conjecture is not true, then we can derive another condition, and so on and so on. Finally, we can say, oh, contradiction. So our original conjecture must be true, right? But in either way, by construction or contradiction, we are going to combine several known properties. For example, when we define the problem itself has some properties. Or suppose we design an algorithm, the algorithm may have some properties. And also we have some assumptions. So suppose the proof is too complicated, we may consider several cases, case 1 and case 2. But case 1, we have to identify the case 1's condition. Those conditions may be valid. So by utilizing this condition or assumption, we can use this property for the proof. And then for the contradiction case, we assume that suppose our conjecture is not true. What does this mean? There must exist counterexample, right? If there's no counterexample, then our theorem, our conjecture must be true. So according to the counterexamples property, we can have some properties. Or by combining some of properties, we can use a derived property, right? By combining all these properties, we are going to get the final conclusion. So I draw a schematic figures, so something like this. So some properties, we can derive another property. Another known properties, we combine them another property, and so on and so. Finally, we can have final result. It's very general idea. Okay, so then we are going to break down some questions. So how to choose the combination of the properties? Which conditions should be? Which properties must be considered together? Or we chose properties already, but what are the relationship among the properties? How to derive the new properties from known properties, right? These are basic questions. Okay, we are going to use optimization for distance. Okay. Any questions so far? It looks interesting, right? Right? So the research must be interesting. So you have to enjoy it. Okay. Yeah, so far I explained the concept only. I'm going to give you example. First, circular balancing problem. So, okay. Let me give you the motivation first. Cake design problem. Suppose we have a cake base and strawberries with different weights and 2 players. Player 1 make a decision to distribute all the strawberries. And player 2 cut the half and take the half of the cake with the maximum weight, right? This kind of setting is very common to make a fair allocation when there are two decision makers. So player 2 enumerate all possible cases, right? And choose the best. Then player worst decision, it must be allocation of the strawberries in a fair way, right? Evenly distributed way, right? So in this setting, what here, so I'm going to formally describe the problem. We have even number of items. Each item has different weight. We are going to arrange all the items on a circle. Our goal is to minimize the maximum sum of items weight over all possible semis. Do you understand the question? The problem setting, right? So we have even number of items. We are going to distribute it as even as possible, right? Any questions so far? Problem definition very clear, right? So I introduced some notation. So I'm going to assume that weights are sorted in decreasing order. Capital W is sum of total weight. Our decision is kind of this circular permutation. And then, okay, so this is the J position, and J plus N over 2 is opposite. Okay. Then we can have some assumptions. So the last item's weight must be 0. Otherwise, we can decrease this amount from all the items. Then the problem nature is exactly the same, and the ratio must be increased. So without loss of generality, last weight must be 0. And item number, we can assume that number of items must be greater than or equal to 6. Otherwise, you can enumerate it in a short time. So specifically, N is 2. There's only one solution, 1, 2, right? And there are 4 items. 1, 3, 2, 4 is optimal solution in any instance. So without loss of generality, we are going to assume that N must be greater than 6. Okay. Now we have an important observation. Item in J's position and J plus N over 2. What does this mean? J is here, J is N over 2. They must be opposite. One important observation is that if you consider any semicircle, 2 items cannot be included at the same time. Right? If you consider all semicircle, this way or this way. Anyway, 2 items cannot be included in the semicircle. What does this mean? From this observation, we can say, oh, if we have very 2 heavy items, they must be placed in the opposite way, right? Make sense? Okay. According to this observation, we can generate very simple algorithm. If you sort in 1 to n, we are going to assign the item in this way: 1, 2, 3, 4, 5, 6, and so on and so on, right? Very natural idea, right? You may think, oh, in this case, this half circle must be the worst case all the time, right? But interestingly, we can prove that just this simple algorithm has a worst case confidence ratio of 6 over 5. Okay. Can we do better? So we just flip number 4 and 3 and 4. So just 1, 2, 3, 4, and then 3 and 4 flip. Then we have 7 over 6 approximation. This is one of the results in the paper. Okay, so now I'm going to show you how to derive this condition, 7 over 6. Okay, so you can think the heavy items are important. Because less heavy items is not that important. So we consider 5 heaviest items separately. And then later, we are going to consider odd item and even item. So we are going to consider sum of even item from item 6 and sum of even item from 6 and odd item from 7. So W odd and W7. Okay. Then now, according to our setting, we can derive validity condition. For example, variable definition. W1 must be greater or equal to 2, W2 is greater, and so on, right? Because items are shortly in this order. And then W even is greater than or equal to W odd. Why? Even. This one is greater than this. This one is greater than this, and so on. So W even must be greater than or equal to W odd. But if you include W5, W5 is greater than or equal to W6, 7 is greater than or equal to 7, so we can say 5 plus odd must be greater than or equal to W. Make sense? And then if you add all together, it's capital W. Okay, so for any instance, this setting must be true, right? These are valid properties. Now we are going to derive some about another group of valid inequalities from the optimal value. So you can imagine item 1 and its opposite position must be something, right? But 1 and opposite cannot be included at the same time. So we want to put W2, right? Then W3 must be placed somewhere. Then there must be semicircle including W1 and W3. Make sense? This 1, suppose it's 2, or if 2 is here, this semicircle contains 1 and 2. If this is 2, 3 must be somewhere, and 1, 3 must be included in some semicircle. So G star must be greater than or equal to W1 plus W3. Make sense? In the similar way, we are going to consider 1, 2, 3, 4, 5, up to 1, 2, 3, 4, 5. We can consider 1, and there are at least 2 items, one up until 2, 3, 4, 5. So we are going to consider least numbers among 2, 3, 4, 5, 4, 5, 1, 4, 5. Some of these items, G star must be greater than this. And similar way, we can derive another condition. So we observe a condition from the problem nature, another set of conditions from the lower bound. Okay. And then this is a solution. Solution 1, 2, and 4, 3 flipped. And we are going to consider all possible cases. And then realize that there are 3 dominant ones. What does this mean? If you choose another one, except this one, that solution must be dominant by one of these solutions. We can prove it. So we only consider 3 cases. This half circle, this half circle, and this half circle. Okay. So far. So condition. This one could be our solution objective, or this one could be our objective solution, or this one. So we are going to choose. We are going to consider 3 cases separately. G1, G2, G3. Suppose this one is our objective function value. What does this mean? Oh yeah, G is this value, and this one is chosen. That means this value must be less than or equal to this one. This blue one must be greater than or equal to this one. Then blue one is greater than or equal to green one, and so on. So if you consider this case 1, then you can derive additional conditions. Now we are going to consider optimal solution. We consider all possible cases. Suppose 1, opposite location is 2, 1, 2, and 3 and 4. 1, 2 is in opposite location. Then you can consider 2 separate cases. 3, 4 are on the opposite location. The 1 and opposite is 3, and 2, 4 are opposite, but 1, 3, and 2, something else. And 1, 4, 2, 3, 1, 4, 2, something else. And 1, something else. These are all possible cases. You are getting bored. How many branching do we consider? So this case, according to the optimal solution setting, we can derive some valid inequalities in each case. Now, how many cases so far? So many. So okay, I said for the solution value from our algorithm, we consider 3 cases. G is G1. Here, 2 is G1. We have this condition, right? G2, another set of conditions. G3, another set of conditions. And G1, case 1, case 2, case 3. Then for the optimal solution case, for each case, according to the optimal configuration, we consider 7 cases. Total 3 times 7, so 27 cases, but this case can be merged. So it's case 1, 2, A1, 2, A2, and so on and so on. So we have 15 cases. I'm going to prove 15 cases, one after another. Okay? To conclude, G must be less than or equal to 7 over 6. How? Let me show you one specific case. Yeah, this is case 1. Case 1. Oh, case 1 is a simple one. Okay. Case 1. Oh, yeah, case 1 property. So you remember G is G1, then G1 must be greater than G2. G1 is greater than 3. We have these conditions. So we have the basic formula. So weights are sorted, W even is greater than, W odd, W5 is greater than, and so on and so on. So this is optimal solutions. This property, we have how many properties we have? 10, 3, 13 properties, right? So our goal is to derive this one, right? And simply, you can multiply some numbers and get this solution. So you can see some conditions are not used. 1, 6, 8, and 29 are not used. So, and you can see all inequalities greater than or equal to, and only there's some negative number, but it's equality constraint, so we can derive this inequality. Very easy, right? You can just add, multiply, and add, right? Now case 2, 2A, 2D, and we have some basic formulas and the case-specific inequalities. We can just multiply this coefficient and get all these results. You can see G must be less than or equal to 7 over 6 G star, and so on and so on. You can just put some numbers and multiply, and that's it. Case 3, the same. Okay? Now, the question is, how can you find these numbers? Okay? So, the basic setting is very simple. We have a bunch of set of valid inequalities. We are going to multiply some constant and add them together, and we are going to derive the condition, right? Right? So, what does this mean? W1, W2 are problem instances. So, any instance we can generate, the maximum value cannot exceed this value. That means there's no problem instance that exceeds this one. Okay? Let me show you the brochure. Okay, so we are going to consider a linear programming model. We are going to consider optimization. We are going to create the problem instance with variable g, w1 to all these variables. Only 7 variables, right? So g, w1, 2, 3, 4, 5, w odd, w even. We are going to define the problem. We are going to maximize z, objective function value, by our algorithm. Subject to, we have to satisfy all the conditions. And then g star must be 1 is for the scaling and non-negativity. And if you solve it, what will happen? I solved it by Excel server. Then W1, 2, 3, 5, and W even, W odd, W, and G is our objective. And then G star was scaled to 1. Then I'm going to put all the inequalities, 1, -1, so that W1 is greater than W2, and so on and so on. These are valid inequalities. These are candidates that we are going to use. And then solve it. Then G must be, G value is obtained by 7/6. Right? Then we can say, oh, our algorithm cannot exceed 7/6. Right? Then how can we derive the coefficient? Do you have any idea? Excluding my lab members, they already have an idea. If you solve the linear programming, what is the byproduct? I'm sorry. If you solve the linear programming, there's a shadow price. Shadow price. So if you, here, these are all the constraints, and there's equation numbers. The equation numbers are sorted is equality first and inequalities. So slightly change it. But for the constraint, we have shadow price. Shadow price gives the information of the coefficient exactly. You can just capture, this 1/6, this 1/8, 5/6, and so on. Those numbers are exactly the coefficient of the valid inequality. Okay. So if you take the linear programming, you have to understand the power, the meaning of the shadow. Okay, so you may think, how can you derive all these conditions? Because I just put all the condition and solved LP and took the coefficient. That's it. Even though we have 15 cases, but it takes just a few hours to get the valid inequalities. So in the paper, I wrote it in this manner. Okay. Yes, so far I showed you one possible case that we can use optimization. There are a bunch of valid inequalities. We do not know how to utilize which constraint should be used, right? By formulating the optimization problem, then shadow price can be used. Okay, let me give you another problem. Flowchart scheduling with outsourcing. Flowchart means each job has multiple operations. Here we consider 2 machines, machine 1 and machine 2. Job 1 has 2 operations. Each operation must be processed in each machine. So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. Okay, so we have set of jobs, n jobs. And each operation has a processing time, Pij. Pij means job J's processing time on machine I, Pij. And this setting, we are going to consider outsourcing option. Outsourcing means instead of execution within the machine, we are going to do outsourcing. Then we can just delete the operation. Instead, we have to pay some kind of cost. So sometimes this outsourcing is expressed as rejection because I can reject some order. Instead, I have to pay some penalty. Okay. So I'm going to assume that if we outsource a certain operation, we have to pay the cost, but the cost is proportional to its processing time. So alpha I is unit time outsourcing cost on machine I. And then we are going to define the set of outsourced operation. So our objective is two. The first one is outsourcing cost. We are going to minimize outsourcing cost because operation ij is outsourced. Pij is its processing time. Alpha is the unit time. Outsourcing cost is multiplication. Outsourcing cost. And also, we are going to minimize the make span. Make span is the latest completion time. Suppose this is scheduled from beginning to the end. This is the make span. However, if you reject this blue operations, so we allow the outsourcing operation level, not the job level. So job 1, 2, both operations are outsourced, but it's operation in stage 1, second stage in job 5 can be outsourced. In such a case, this is the max. Okay, so if you outsource more and more, max span will be decreased, right? Kind of trade-off. So our objective is max span and total outsourcing cost. First of all, is it hard? So one of my paper in long time ago, right? Okay, some of you are in elementary school. Okay, so according to the value of alpha, the problem is NP-hard and problem is solvable and so on and so on. So here today, I'm going to focus on this type 2. When alpha is between 0 and 1, beta, alpha 1 is 0 and 1, alpha 2 is 0 and 1, but some of these two is greater than 1. So you have to be very careful. If you, sometimes if you reject some operation, but max span is not decreased, it's useless, right? But if you reject max span is significantly decreased, you may want to outsource some operation, right? Okay, so we are going to consider very simple algorithm. Suppose, without considering outsourcing, we have an optimal algorithm to allocate all the operation to minimize the max span. It's called Johnson's rule, but you don't have to remember it. So suppose jobs are sorted on a certain manner. What is the ideal image? Ideal image. So when alpha 1, alpha 2, each one is less than 1, if you outsource this much, decreasing amount is its processing time. However, alpha times processing time must be less than or equal to original processing time. It's beneficial, right? So we are going to outsource. It's always beneficial. But the idea is, oh, there's some jobs in the middle. So we may scratch our head. Should we outsource this one or not? Right? In the same manner, this one, I want to outsource, and oh, should we outsource or not? Something like, right? Ideally, if you cut and outsource, we will be very happy, right? If you cut, because if you alpha 1 plus alpha 2 is strictly greater than 1, we want to both. We don't want to outsource both operations at the same time because outsourcing cost must be greater than max span decreasing amount. Make sense? This is the setting. So idea is alpha K1, we can define K1 and K2. Ideally, we can cut it and partially outsource, but it's not possible. We are going to consider some possible cases. Sometimes you want to outsource K1, 1, K2, 1. So I consider all possible cases, 4 cases. This one, and include this one, or this one and include this one, this one. So 4 possible cases. I include, enumerate 4 schedules and choose the best. Algorithm description is quite simple, but analysis is not that easy. So I'm going to simply introduce some notation. Let's say here, L. I want to outsource this much ideally. Let's say L, left side, R, right hand side, in the middle, X. So there's some, so also the processing time of K1 is PK1, this is capital P1, PK2, P2, and so on. This is notation. So we can consider 4 possible cases. And then, so this is kind of ideal case because outsource this much. So our pain, we are going to pay alpha 1 times L and alpha 2 times R. This ideal outsourcing cost, and in the middle is a contribution to the max plan. This is ideal case. This is a lower bound. This was previous paper, and we are going to consider this case. Okay, what can you do? So we derive some conditions. So by symmetry, we can derive 1 cases. H3 is always greater than with H4. So we have these cases. So suppose if you consider case 1, what does this mean? H1 is our objective. H1 is the minimum among others. Then we can derive another condition and so on and so on. So also we have additional property from the structure of the solution. What does this mean? P2, this P2 and PK2, this blue part, must be less than or equal to X plus R. Yeah, according to the structure of the schedule, we can derive some condition. Then we consider soft cases. Case 1, case 2, within case 2, case 2-1, 2-2, and so on. So draw the figure. As I said, alpha 1 and alpha 2, it should be, each one should be between 0 and 1, but some of these 2 must be greater than 1. So this right upper triangle is the range of alpha 1 and alpha 2. Then this condition is case 1, case 2-1, 2-2. Then I'm going to, so yeah, from the previous paper, we have validity inequalities. We want, as I said, this is the lower bound of optimal max plan, optimal objective function value. So we want to have similar form of this by combining all the previous cases. So let's say equation 5, we are going to multiply alpha 2 squared. Equation 6, we are going to multiply 1 minus alpha 2. Then by rearranging it, but case 1 says this value, alpha 1 is greater than or equal to this one. So we have this condition. This is what we want. Then we can say this is our objective function value and multiply something is less than or equal to optimum value. So the ratio, approximation ratio, must be 1 over this value. But according to range of alpha 2 is bounded by 4/2. So we are going to combining all the validity inequalities, and this is what we want. In the similar manner, case 2, we have 1, 2, 3, 4 here. it's kind of basic inequalities that we are going to use from the cases and another valid inequality from the structure. So we are going to multiply certain non-negative coefficient and multiply, and we have something that we want, then something additional. Then we can prove each value should be less than or equal to 0. We have this one. So in the same manner, we can prove this bound is 4. This value is bounded by 4 over 3 has optimal value. Last one, case 2-2 is complicated, but our goal is to derive this one. Oh, not this one, but we try to make it as close as possible. Then we can conclude that this G1 is less than or equal to alpha 2. So X, alpha 1L, alpha 2R, then something others. This must be less than or equal to, so we can prove it. But it's not yet proved because y1 plus y2 plus y3, these are coefficient. So we have this setting. We derive up to here. The problem is we do not know y1 plus y2 plus y3 is indeed bounded by a certain value. So we define an optimization problem. So this must be the 1 over this value in the coefficient of the optimal objective function value. So we are going to meet by this value, and alpha 1, alpha 2 should be less than or equal to 1, between 0 and 1, alpha 1, alpha 2 greater than 1, and the conditions for the branching. By using this one, if we solve the optimization problem, then finally we can get this value is bounded by 3 over 4. So we should consider this reciprocal. So 4 over 3 is found. So this is another application. Sometimes we have very complicated values, but we do not know its bound. Then we can formulate it as an optimization problem. This is a simple nonlinear programming problem. You can solve it, then we can get the bound. Now, another example. This is ongoing work. These two problems are already published. This is ongoing work. One of my PhD students is working on it. Multi-fit algorithm. So, it's about the parallel machine scheduling. So its motivation is that many systems require allocation of jobs to multiple machines. So let's say there are a bunch of jobs. We are going to allocate this job to the machine. Yes, but we are going to measure the schedule by the latest completion time. Is called makespan, right? So what is the reasonable algorithm? This notation. We have n jobs. Each job is processing time pj, and each job must be processed in each machine. And we have identical parallel machine, m identical parallel machine. So the latest completion time is denoted by makespan Cmax. Okay. So this problem is known to be strongly NPR long time ago, and there is a approximation algorithm. For example, LPT. LPT's bound is quite good. Over 3 minus 1 over 3m. But some people consider another idea called multi-fit. The idea is like this. So we are going to schedule jobs in this way, but we are going to flip, rotate it in 90 degrees. We can consider this kind of beam packing problem. There is a capacity. This capacity, we are going to assign job. And the number of beams used is less than or equal to the number of machines. It's fine, right? Then this capacity plays as a makespan, right? If you succeeded, then you can decrease our capacity. And if fail, we can increase it. By bisection method, we are going to reach the bound. So this is idea. We have a always successful bound, upper bound, always the invisible lower bound. We have an upper bound and lower bound. Then if you solve the problem, it succeeded, we can decrease the bound by set this one and increase the bisection method can update the upper bound. So let me give you an example. Suppose this is a set of jobs. 1, 2, 3, 4, 5, 7 jobs. So if you consider its lower bound is 7, upper bound is 14, then average is 10.5. Let's say 10 is our target. And with 10, we can assign 5 here first and 4. 3 is not possible, so 3 is assigned here. 3, 2, 2, 2. We can succeed it in assigning all 3 jobs. We can decrease capacity to 8. So 5 and 4 is not possible for here. 3, 3, 2, 2, 2, right? Then again, 7, 5, 4, 3 is here, next 3 is here, and 2, 2, 2. Succeeded, and it's impossible to improve it. So this is solution. In this particular example, multi-path algorithm gives us an optimal solution, but in general, it's not optimal algorithm. There's a known bound. So when number of motion is 2, 8/7 is the bound. 3, 15/13, and number of motion is 4 to 7, 20/17, and number of motion is 13, and 13/11. But there's a gap when number of motion is 8 to 12. Upper bound is known to be 13/11, but there's a bad example. It has a 20/17, so there's a slight gap. We do not know which one is the right gap. So we try to solve it. It's not practical. We just from our curiosity. Okay, so how can we solve it? We are going to use the contradiction idea. We believe the lower bound is the right bound. Okay, lower bound is right bound. That means we believe that 20/17 is the right bound. So we, to obtain this result, we propose optimization-based verifier. This is a kind of tentative name, OptiVeri. I'm not happy with this name, but anyway, this is current name. So we are going to use mathematical optimization to validate this approximation ratio. So we have to use the computer-assisted evidence that the claim bound is correct. So the idea is as follows. Suppose this bound is not correct. Bound is not correct. What does this mean? There must be counterexample, right? So we try to formulate the mathematical programming model to generate the counterexample. Okay. So J is a set of job, M is the set of machines. So algorithm is max span by algorithm on instance I. It's optimal max span. So as I said, we are going to use contradiction. Our claim is approximation ratio is low bar. But suppose, assume that approximation ratio is strictly greater than low bar, then there must exist counterexample, right? So let JCE is a set of all counterexamples. The counterexample cannot be empty. Suppose counterexample set is empty, that means it's impossible to find an instance, right? So we are going to formulate optimization model. So opt is the denominator, multifit is the numerator. So I is the variable, right? We are going to generate the problem instance within the counterexample set. Okay, so if you solve this problem and the optimal objective function value, suppose the counterexample set is not empty, we can find out an instant. Then each objective function value must be strictly greater than low bar. And if we find an example, that means, oh, our original guess was not correct, right? Okay, but the issue is that this counterexample set is intractable. It's hard to define. So we are going to consider another concept. Let's say, this is important idea. If there exists a counterexample, there must exist minimum counterexample. Philosophically correct, right? If there is a counterexample, there must be minimum counterexample. So we consider the minimum counterexample set, but minimum counterexample set is not easy to describe. We define the superset of minimum counterexample set. Then, based upon this set, we are going to minimize the optimization, maximization problem. So, based on the assumption, processing times are sorted in decreasing order, normalization, optimal max span is 1, and we define low counterexample. What does this mean? If you put the target approximation ratio low, our first bit decreasing algorithm must fail to assign all the jobs. Okay. So minimum low counterexample. What does this mean? We have several properties for the minimum counterexample. Suppose we have a certain job. P1 is assigned here, 2, 3 is not possible, so 3, 4, 5, 6 is not possible, 6, 7, 8, 9, and 10 is not assigned, 10, 10, 10. Suppose 11, 12, 13. So 10 is the first job that cannot be assigned within this row. Then you can just eliminate all the following jobs. It's still counterexample, right? Because by eliminating some jobs, max optimal value cannot increase, right? So without loss of generality, if you consider minimum counterexample, the last job cannot be successfully assigned. There's no more jobs. Make sense? This is a very common argument in the minimum counterexample. Because if you assume the minimum counterexample setting, we don't have to worry about the following job. We can say the last job failed. Before that, we succeed assigning all the jobs. Make sense? Okay. With this property, then we have to identify the problem instance. How? Here, when machine capacity is low bar, in our case 20/17, all jobs except the last one are assigned in first bit decreasing, right? The last job cannot be assigned, and optimal max span is 1. How can you formulate it? So we have to consider two settings. In optimal solution, we have to assign all the jobs with max span of 1. In first bit decreasing, except the last job, all jobs are assigned successfully in first bit decreasing way, and the last job must be failed, right? We have described everything with mathematical formula. Okay, we have processing time is a decision variable, PJ. And also, machine assignment in the optimal schedule is also decision variable. So we are going to use Xij. Xij means job J is assigned to machine I. then multiplication of pj times pij means contribution of job j on machine I, right? So if job j is assigned to machine 1 and p1 j must be 1 and so on. If job 2 is assigned to machine 2, x2 must be 1 and so on. And we have to say all the job must be scheduled in this manner, right? And we have to encode the multi-fit. It's a little bit tricky because we have to capture every moment when job is trying to be assigned, right? So we introduce the notation Bij. Bij means the after assigning job J, the total load on machine I. So when machine job 1 is assigned to machine, because the first bit decreasing, we have to try the first available machine and it's fed and try the next machine. So job 1 is assigned to machine 1. We are going to use Qij is the jobs assignment to machine in first bit decreasing. And job 2 is possible. So at that time, Bij must be P1 plus P2 and so on. P3 is not assigned in machine 1. So P3 is assigned to machines. And then Bij is updated to P3 and so on. And then suppose we have, okay. So P9 was not possible, 9 possible, and the last job should remain. It's not possible to just say. So as I said, Pj, you can, when we formulate the optimization problem, we define the variable carefully. Pj is the variable, processing time. And Xij is the variable. This is the optimal solutions allocation. And Qij is in first bit decreasing. And Bij is the auxiliary variable. It's a cumulative load on machine I after job J is assigned. And that last moment, so we have to check the last job cannot be assigned the machine, all the machine within the capacity. So we only consider Bij up to J is less than or equal to J minus 1. Then consider last job separate. Okay? Then this will give us a kind of objective function value. So see, processing times are sorted in decreasing order. And then Xij on summation on I, what does this mean? Job J must be assigned one of the machine exactly. What does this mean? Pj, Xij, the multiplication is a contribution of job J on machine I. Summation on J is the total load on machine I. It must be less than or equal to 1 because optimal solution, optimal maximum must be 1. And for the multi-fit, job must be assigned one of the machine. So this is the cumulative one. Job J is assigned machine I, Bij must be updated in this manner. And each Bij is bounded by this value. This is quite interesting part. So if job J is job Qij is 1. What does this mean? Job J is assigned to machine I. That means job J cannot be assigned to machine 1, 2, up to I minus 1. It tried, failed. Why? It exceeds our capacity. So this is the expression. Then the last setting, when job can try all the machine independently, it cannot be assigned within our law, but we just put the parameter here, another variable, we are going to maximize it. If you try to solve this problem optimally, if this G value is strictly greater than low, then our approach is failed. But if you solve this problem, optimal objective function value is less than or equal to low bar, that means there's no instance like that. So we can say it's contradiction. Okay. So how can we solve it? Oh, by the way, what is n? We have specified m, right? M must be 8 to 12. But how can we specify n? Order n. So, but nicely, from the minimum count example, we can bound some range. N must be this value. So we are going to enumerate all possible cases. I like enumeration and case spreadsheet. So a specific m, we have range of n. We choose one specific n. So fix the m and n. We are going to solve the verifier. M and n, target no bar. If you solve this problem, it's strictly greater than no bar, then our approach will fail. But this problem is infeasible where each optimal objective function value is less than or equal to low bar, then we can say it's contradiction and our correct. But in this setting is correct. However, computationally, it takes so long. Even m is 5, it may take into m is 5. If you solve this original problem, it may take 1 week. Yeah, it's impossible to solve it. So we have several case branchings. You can consider some last job, the smallest jobs condition. If the last job is greater than equal to a certain value, what does this mean? All jobs are quite large. And the last job is too small. What does this mean? So the gap here, this gap cannot be that large. So it also gives another restriction. So according to the setting of the last jobs case, we have some cases, and each case, according to this case, we have some structural property. For example, in case 1, last job is quite large, then we can derive some properties. Suppose multiple solution must be, we can define long job, this heavy long job and short job, long job, and the submachine can have only 2 long job or no long job. And no long job machines always have at least 3 short job, and so on. We have some additional properties. In optimal solution, each machine has at most 1 long job. And so those properties can be derived, and we have add a lot of condition and solve the optimization problem. Experiment Ubuntu, we use Groby, and then finally we can get our conjectures correct. So it takes about 3 days. But in the previous setting, in number 7, if you solve just formulate it, solve it, takes a week, we cannot get the result. But by case branching and valid inequality, we finally get the result. I want to mention that the Gary and John, do you know Gary and Johnson? They are famous guys in this field. And Kaufman, Gary and Johnson, they first proposed this multi-pip approach, application of bin packing to multiprocessor scheduling, right? So it was published in 1978. The proof of the upper bound m for m less than or equal to 7 involves case analysis which grow more and more complicated and increases. These proofs have been omitted at suggestion of the referee. There's no written proof in the paper because it's too complicated. So, but the full version of the paper containing them is available from authors. But unfortunately, all 3 guys are retired. Right? Or dead. What? Really? 2 retires, 1 passed away. Okay. It's not available. But see, with just less than 20 seconds, each case can be provable. So they said they shall omit, limit ourselves here to proving generally. So even though they say in the paper, they only prove the case, the m is 4, right? There's proof on m is 4, but 5, 6, 7, there's no written proof. They just claim that we proved it. The referee said, oh, it's too complicated. So it's not published in the program. So, okay, byproduct, we found out some IT examples looks ugly. Okay, for this third approach, we propose optimization-based verifier for the contradiction. We try to generate our count example, and then this idea can be extended other cases. Okay. Conclusion. Oh, I stated about time limit, but so far I showed the three cases. I can say the procedure of the proof is to derive desired property from known properties and combining them together, right? So the first case, a circular balancing problem, you remember cake cutting, right? So this one shows how to choose the combination of properties. Example 2, flow shop with outsourcing, right? Some complicated numbers are put as a coefficient, but we can easily calculate its upper bound by formulating as an optimization problem. It shows us how to derive the new properties from known properties. The last one is the how to construct the minimum counter example approaches. But nice thing of the counter example is that if you assume the counter example, there are more properties of the counter example, so you can utilize them. So this one is one of my PhD students and his work, and this is my another PhD student's work. This is my current PhD student's work. Okay. So I have some lessons. To derive a critical property is still a core idea of the proofs. However, tedious part can be expedited by optimization. So here I said, oh, G must be G1, G2, G3, right? This case branching, right? This one can be done by expert, by you, right? But each case, subcase combination, this case, how can you do it? But this kind of tedious work can be replaced by optimization. For the critical property, this is kind of some clue. So consider nice case spread. For critical property, you can consider nice case branching. For example, you remember, right? So case 1, 2, 3 for the G. And for the optimality, we consider this 7 cases. And for the multi-fit, the last job will determine the characteristic of the problem. So according to this choice, can be done by a researcher. And also, you can consider very ideal case. You remember this outsourcing case. We know very, very ideal case. This is our lower bound of optimal objective function value. We try to modify our known result and make it as close as possible. Then consider the remaining. This is one possible clue. Okay, this is end of talk. Thank you. Any question? You can ask in Korean. Okay, I think you want to go home. But I want to say one more thing. Here, optimization is very useful tool. So some of you directly utilize optimization in your research but many problems especially in engineering field can be modeled as an optimization. If you have this kind of aspect, it will be helpful. If you do not know how to do it, you can grab some people in industrial engineering people and okay, thank you for your attention.